Hello and welcome back to another video. In this problem, we're told if h is the Heaviside function defined in example 2.2.6, using definition 2, find that the limit as t approaches 0 of this function does not exist. So the Heaviside function, h of t, is equal to 0 if t is less than 0, and 1 if t is greater than or equal to 0. And we're looking to see that the limit as t approaches 0 of this function does not exist. So we're going to use the precise definition of a limit, which states that the limit as x approaches a of f of x, this is a limit if the absolute value of x minus a, so the value that t is approaching, is less than some number delta. If this is true, then the absolute value of h of t minus the value of the limit, which we're calling L here, is less than epsilon, right? And the idea behind this is basically for any epsilon we choose, there's a delta for which both of these inequalities are true. So what we're saying here is that we are picking epsilon as 1/2, right? So the absolute value of h of t minus L is less than 1/2. Therefore, we are saying that for some, for the absolute value of x being less than delta, for some distance delta, right, away from 0, there is a value, and this should be t, I suppose. There is a value of h such that h of t minus L is less than 1/2 and greater than negative 1/2. Adding L, h of t is less than L plus 1/2 and greater than L minus 1/2. So what we're saying here is there is some, looking just at the number line, we have t is equal to 0 here. There is some distance as we approach 0 for which the value of h of t is in this range for all values between negative delta and delta. Is this true? Well, we know that no matter how close we get to h of t, graphing it here, right, the function looks like this. We know if we're 1 away, we have points that are equal to values of the function that are equal to 0 and 1. If we go half away, there's values that are 0 and 1, right? 1/4 away, 1/8 away, all the way down. No matter how small we make delta, there's values of the function that are equal to 0 and 1. So what does that mean? Let's say L is equal to 0.5, right? Or let's say 0.49. Right? If this is negative 0.01, then these points are all going to be included within this range that h of t is allowed to be in. And I picked 0.49 because it just barely gets there. And here we have 0.99, which means none of these points are valid points. Right? No matter what distance we are from 0, we're going to have points that are equal to 0 and points that are equal to 1. So what we need to do is say, okay, if the function is between L minus 1/2 and L plus 1/2, right, the difference between these two, L plus 1/2 minus L minus 1/2, this is equal to L plus 1/2 minus L plus 1/2 is equal to 1, right? The difference between these 2 points is 1, right? As you can see, the difference between these 2 points is 1. So the sort of best case scenario would be if we had less than or equals to, sorry, I did that over the L. H of t is less than or equal to L plus 1/2 and less than or equal to L minus 1/2. Why? Because if we did that, then the difference between these 2 points would be 1. They'd be valid points, and 0 and 1 would be allowed to exist here. However, it's not less than or equal to, it's just less than. So the difference between the highest possible point and the lowest possible point within this range is not 1, it's just slightly less than 1. So therefore, no matter how close we get, since we're still going to have points that are equal to 0 and 1, we are never going to be able to say that all values of h of t in whatever range we choose are between L minus 1/2 and L plus 1/2, because it's simply too restrictive of a range in terms of the size of the range, regardless of what value we pick for L. Right? If we say, okay, let's allow 0 to be in, 1 is going to be cut out. Right? And you can add as many zeros as you want here, as many 9s as you want here, you're still never going to get to 1. Therefore, this limit does not exist.